All right, welcome back. I think to kind of wrap this set of notes up, we'll try and look just real briefly at other extensions of this like Van Driest model and analogy. And I'm going to kind of go fast through these pages because I want to focus on practical predictions with Cebeci-Smith model, which they put in an axisymmetric form and reduced to even a simpler set of equations, a differential equation. And so from the previous recording just now, we have this expression for A as a function of A plus, etc. And that would actually be put into the length scale model, which was proposed by Van Driest. So here's the Cebeci-Smith model. And in just practice, you can make this substitution, and now you have a modified length scale. And you see it's incomplete because you're basically specifying your length scale before you've solved the problem. So you're kind of introducing a new equation that is kind of restrictive because it's saying the length scale must go in this form, which maybe not accurate always. Anyway, other people kind of picked up this work of Cebeci's extension and try to improve it even more. And so here's the Cebeci type model. And here's one which was put out by Prandtl and Spalding in 1967. You'll see this name Spalding a lot in the research area of the 60s and maybe 70s, I think. I don't remember exactly when he's active, but here's just a simpler damping concept, a little bit simpler than a Cebeci-Smith model. And let's just make some notes about it. And first of all, they reasoned and just wrote this equation that there's some damping of turbulent fluctuations are more likely to be influenced by local values rather than wall values. So Cebeci's method, he was looking at statistics at the wall because that's what he cared about, and maybe boundary layer thickness. This is maybe a little bit better model because it's saying that what's happening in the boundary layer is a local property and not something, maybe some property of the boundary layer itself. So they would say for A, they replace tau w by value of tau. So that's just the stress instead of the wall stress, because it should vary. And they set A plus equals 26, which is a good value to set just based on comparing your predictions of experiment. A plus 26 goes as, say, partial p, partial x goes to is about 0. And they also assume that, say, kappa goes as about 0.435 in their calibration too. So that's a little bit lower than other people. And so that was a whole model in itself. They just basically used the Prandtl-Spalding model, just used this length scale with a modified value for A, set 26 as a constant, and if they wanted pressure gradients, they could vary it. And kappa 0.435 validated comparative experiments. It's an interesting thing because they just got away from wall statistics and local statistics. Another set of authors, K's, in 1970 paper, used this equation 445 and modified it to calculate flows with mass transfer. And they expressed this damping coefficient A plus as a function of the mass transfer parameter and pressure gradient parameter P plus. And so they gave a new definition of A plus. And look at this form. When I look at an equation like this, I'm like, well, where did this come from? And they just wanted to use this Spalding's model, which didn't use wall properties, and put it in a general form where there's lots of coefficients, and they calibrated these coefficients against a huge range of experiments. And of course, when they used their model to predict flows with these lots of empirical coefficients, which I've listed here, it agreed really well. And they were happy, but then they exercised their model outside their range of empiricism, outside the range of validity, and it wasn't predictive at all. So they used something, I think, a successful idea of using local properties instead of wall properties like Cebeci and Smith, but then they introduced a lot of empirical parameters to fit a wide range of data, but they couldn't get outside that range. A few other authors kind of explored similar approaches. One I wanted to note is Nicole and Strong and collaborators. And they basically also took the solution of the Stokes problem, and they added in a mass transfer term. So some people wanted to explicitly account for mass transfer through the wall, and that's another analytical PDE, and they chose this form because it has an analytical solution. U naught prime times exp of negative y over square root of 2 ys, once again, times cosine omega t minus ys us, all of the square root of 2 velocity term. So, here's ys, and then there's us here. And so it's the exact same solution as before, but us and ys are way more complicated because of the introduction of this mass flow term. Once again, they saw that there's similar fact terms in these equations, and they equate them. And they find this relation that must hold between ys and us. So if you set one, you should set the other one accordingly, or you're not going to get a good prediction. And they can also just reduce their whole system and have no mass flow rate, but I don't think that's very useful after you've gone all that trouble, because you could just use Cebeci's or Spalding's model. So another thing maybe that was interesting that was done is Nicole and Strong using equation 4.55. And let's just scroll up. So that's your typical A+ model with Spalding, which is local instead of wall-based. Sorry, I got mixed up here. There we are. They basically inserted it to the right-hand side. So this is the original. This is 4.55 essentially. They just added 1 over d plus and proposed this d plus factor, which is another huge empirical term. And all this in here is empirical coefficients, which are calibrated. This is a wall mass flow rate. And this modified A, which is substituting A+, which is substituting A++, which goes back into the Van Driest model. So you can see it's becoming insane. And that's how a lot of these algebraic models are. People keep adding empirical terms to try and make corrections for mass flow rates, and this one is like a deficit term. They call this a deficit term. And many substitutions of A. And it's frustrating to me because when you look at the literature and look at all these models, and some of them were used a lot for design, a lot of them just kept adding empirical factors and calibrations to make predictions. But this only goes so far. And I think what the message here is these models are only going to take you in a place, and to do more like physics prediction, you need to have additional differential equations like we showed in earlier classes, like equations for turbulent kinetic energy, for example. Okay, so with this section, these are notes just on all the different boundary conditions you have to apply for all these empirical type models. So of course, when you add more empirical terms, then your boundary conditions are going to change too. This last thing, I don't want to spend too much more time on this section because it's just basically adding empirical equations on top of empirical equations on top of empirical equations and writing journal articles about it and running them in your CFD code. And you can do that all day without much progress. I did want to show one quick figure, and this is this little A plus term on the y-axis, and this x-axis is your basically mass flow through wall, or proportional to it, is it's at the wall, it's incompressible, and this is just the velocity at the wall in inner coordinates. And people were actually estimating, well, they were drawing the curves of their model, which are the solid lines. And there's some measurements that were trying to estimate these values. And these were actually done at LARC, NASA Langley, to confirm these models of Cebeci and Smith. This is a publication of Cebeci, 1973, and the experiments were done by Bushnell and Beckworth. And this graph, I think, is kind of interesting historically, but I think what it shows is that at least they were finding somewhat of the right trends of these Van Driest type modified models. The historical note is there's this Bushnell author, and he was a NASA Langley researcher, and he's still the chief engineer, or excuse me, chief scientist of NASA Langley Research Center today. And so way back when I was a new employee, a few years ago there, he's one of the first people I met with, and it's kind of funny to still see his name. He's quite old now, but an interesting character. With that, what I want to do is like refocus our work to be something a little more practical. And at this point in the world with my cell phone, if I could run the full Cebeci-Smith model, I wouldn't have to do anything else. I would just have a computational grid, and I would have a laminar Navier-Stokes solver. I would have the Navier-Stokes-Rans based equations. And I would have another equation, my algebraic equation, which would be what? L. And L equals kappa times an exponential factor involving A. And I would replace A with the A plus equation. I'm done. That's the equations I saw for Cebeci-Smith in the simplest form. But back in the 1970s, which I don't think any of us were alive in the 1970s in this room, they didn't have such luxuries of technology. And they wanted to solve simple differential equations very fast over a whole aircraft instead of saying millions and millions of grid points like we did today. So say you're in this situation where you maybe have less computer power than an Apple I. Very limited things. Access to supercomputers was limited, and you would have to use them to solve your equations in flow fields. And you would try and want to reduce these equations to even a simpler form. So what would you do? Well, you can always make another assumption and say, well, we're going to first look at our flow fields over long, slender vehicles and approximate our vehicles as being axisymmetric or locally axisymmetric. And so the idea is to recast my general equations into an axisymmetric set of equations and try and reduce that set of partial differential equations into a single differential equation involving, say, like a function f. So that's what we're going to look at real quick here. So we're going to look at this Cebeci-Smith model applied like they originally did to axisymmetric laminar turbulent boundary layers that are slender over slender vehicles. And this has been explored in a lot of codes for maybe a decade of time in the 70s, late 60s and 70s. And they're highly accurate, and if you ran them today, they'd run in like in, a finger snap. They'd be done before you would release the key, because they're so fast today. So let's just look at, and I kind of discussed the notes verbally, so that's, you might, hopefully you've been jotting a few things down I said. So let's look at our governing equations. We have the continuity equation, that's mass, momentum, and total enthalpy. That's what we'll choose. We have Prandtl number, non-dimensional, and we have R here. And in my notes, we'll set K equals 0 for 2D, and set K equals 1 for axisymmetric. And you can see that way they didn't have to work with two different codes. You just use one computer code if it's a 2D or flow versus an axisymmetric type flow. R is, of course, the radial distance from the centerline axis of your vehicle. Mu is your average viscosity, which can vary. And they have boundary conditions, and they apply the exact same boundary conditions for boundary layers, which we talked about. So here's your x, that's the streamwise distance. V, of course, is the cross-stream velocity, and it's axisymmetric, so W bar would be reduced to 0. And as we get very far away from the wall, we would have an edge velocity. And you see that's a function of x, because we would suspect that the velocity at the edge of the boundary layer changes as we move along our aircraft boundary layer. They have the same type of boundary conditions for total enthalpy. Now there's a reference velocity u infinity. That's like basically the speed of the aircraft at altitude. And these are the edge velocity and enthalpies. So those are the major equations. I jumped ahead of my notes a bit, sorry. Yep, and I've already said some of these things, but x is streamwise direction. And these are going to be transformed down into a coordinate system like we show in 4.3. And you see this figure here, or a variation of it, shows up in the journal articles I passed out for Cebeci-Smith. So now they're going to transform their coordinates so that this is essentially the x direction along the body, and the y direction is at the local boundary layer location. And some of you who've done these types of calculations see the advantage of making your grid orthogonal to your surface, because that way your equations exactly line up, and you might be able to do a marching solution. So these are the notation, of course. Y is cross-stream, or R. You can use them interchangeably, essentially. Another thing you'll note for these high-speed boundary layers is the profile. So they've drawn in their figure correctly the profile of, say, velocity, but you see there's actually a max value of total enthalpy or static enthalpy within the boundary layer. So if this is the boundary layer edge here, you can see there's a max of enthalpy. And that's very common in high-speed turbulent boundary layers too. Okay, so those are our major equations, which are just listed at the top of the section. And we can use the closure scheme, which was previously discussed, and we'll have negative rho u prime v prime. Reynolds stress goes as rho bar times our eddy viscosity times partial u partial y, simple. And the second one we need to close is it's a compressible flow. We haven't really talked a lot about it. Rho v prime h prime. So this is the basically velocity fluctuation times the fluctuation of total enthalpy. This is, if we wrote the equation the exact same way as the top part of equation 4.1, we would have a term like this, but it's really hard to model something like an eddy viscosity for an enthalpy term, so they just simply wrote it like this. Rho bar epsilon m over the turbulent Prandtl number times partial h bar partial y. By analogy. By analogy. So the second part of 4.81 has something interesting. It's saying that this relation between velocity fluctuations in the cross-stream direction and total enthalpy go as an the same eddy viscosity as the Reynolds stress closure. So that's an interesting choice. And it turns out to be a really, really good choice. You can check it. It's dimensionally correct. And for predictions, it works really well. And I wrote by analogy because you can see there's a density term, there's the eddy viscosity term. PRT is going to be 0.90 approximately. Oh, I wrote that right here. Isn't that nice? And they just use basically the derivative of enthalpy, the mean enthalpy, just like they use the derivative of mean velocity. by analogy. So that's the closure. And then you say, well, how do I find epsilon m? That would come from our length scale closure, because we're essentially saying something about length scale in advance. Okay, so those are the equations. And now we want to transform them into something that can be solved. And he not only used one transform, but he used a transform on a transform. And that sounds insane, but you'll see that was a great decision, because he's going to reduce this complicated set of equations in 2D or axisymmetric flow around slender bodies into a single differential equation, which is uncoupled from the enthalpy equation. So we'll have two ODEs, and they're going to be decoupled. And if you have an ODE, a single ODE that's decoupled for the boundary layer profile, once you solve that numerically, then you would solve the second ODE numerically based on the first solution to find the enthalpy variation. And you can do this extremely fast as you march downstream on complicated aircraft like an F-18. Amazing. Anyway, let's look at these two transforms quickly. I just want to kind of get through the major points of this so we can talk about the papers on Thursday. So I'll kind of do a highlighter here. The first transform here, solving these equations with already closure coefficients, is called the Mangler transform. And that's taking your differentials in x and y and putting them as x bar and y bar. L here is a reference length. So sometimes you might choose that as just the distance downstream from the aircraft leading edge. And so that's the first transform. It involves R and LR. K, once again, is 0 or 1, depending on if you're in 2D or axisymmetric. And then they use another transform, which is called the Lévy-Lees transform. And these were pretty well known before the advent of computers, because we didn't do as many transforms. We just do like these Jacobian transforms for grids today. That related this bar x and bar y from 482 into d psi and d eta. So what happens when you do this? Well, they allow for the calculations to be very easily performed. Which is the whole point of it. And in fact, this transform boundary layer thickness is going to be constant and similar in all laminar flows. So his model will reduce to a laminar flow solver in certain situations. And those solutions, if you let it be a low speed flow, like below Mach 3, they would give you the Boussinesq solutions. So that's probably a good reason for doing these transforms, that it reduces to some analytical solution you already knew. Also, it's really difficult to capture compressibility effects. And it turns out that just the numerical solutions turn out to be stable on low precision computers. Which is another thing you got to think about when you're trying to create a turbulence model. There's been a lot of turbulence models that have been proposed, but they're impractical, because when you program them, well, they might be very, very difficult to program or kind of not really nice numerically. Anyway, we're going to combine these particular transforms, 482 and 483, and we'll get a relation between d psi and d eta as dx and dy. So we can take that and just call it a Mangler-Lévy-Lees transform, and also introduce a stream function, because you can look for stream functions. You say r to the k rho u equals partial psi partial y, and r to the k rho v equals negative partial psi partial x. So psi is the stream function. And it was really common for people to look for stream functions and solutions, and it makes sense here. And they related these stream functions psi, which is a function of x and y over the boundary layer over the vehicle, as 2 psi to the half times LRK times f of psi eta. So you see, this is really our unknown variable. And we're going to take all this and define the partial derivatives. Partial x with respect to y, and partial y partial y with respect to x. And this contains all our transform variables with respect to stream function here. And anyway, you can see where this is going. It's a lot of work that he did to transform all these equations now to this form. And the primes are derivatives with respect to eta. Now he also makes use of the energy equation, Euler equation, and he comes up, after combining all these transforms with a stream function, into these two equations. And this is listed in papers, which I don't think I distributed to you because they're less general. But let's just take a second to appreciate all these transforms that were conducted. So this is an equation for momentum. And F is the unknown, and F is really a function of psi and eta. And those can be related back to x bar and y bar, which would be related back to x and y. So if you can solve this differential equation with appropriate transform boundary conditions, you just simply back substitute through these two transforms we did, and then you find your original field variables involving, u, v, p, t, rho, and I guess your total enthalpy too. So, but by doing this work, you'll see in 492, there's really one unknown, and that's F, which is cool. This is also similar to the Faulkner-Scan equation, and that's where he got the idea to do this. Because originally the Faulkner-Scan equation was a type of an equation that you could solve for boundary layer flows. So this didn't just come out of thin air. These same type of transforms were used on the Navier-Stokes equations to get that equation. So now you can say, okay, well, this equation only has one unknown. Now look at the energy equation. What are the unknowns? You have F and G. Now G is also a function psi and eta. And so to solve the system at any position psi, I would march downstream with, say, a known condition, and I would march downstream and solve for this differential equation at, say, psi at I plus 1, right? So in a flow over an axisymmetric body, I go this direction, I know this profile, and I march downstream at I plus 1, where this is the psi direction, and this is the eta direction. And this is your body. So my first step would be solving equation 492 for F, and then I could recover field variables through back transformation. And now I know F in 493, and I would solve the differential equation for G. And that would give me all my variables at a profile location. Now think about the solver you're developing for the computer project. You're right now marching in the x direction, I think, or time, it doesn't matter. You're marching in one direction, and you're taking derivatives in the cross-stream direction. So you're essentially building up the exact same type of solver that someone like Cebeci-Smith developed, except he's dealing in transform coordinates, and you're not. You might use a grid stretching transform instead of a transform on an equation. So you can see kind of a direct analogy between you're doing your computer project and what he did. You're setting a initial condition, and you're marching downstream with a implicit solver. So he could also do the same type of marching algorithm. Anyway, for completeness, for these equations, we have listed all the little variables in there. So technically, you could sit down and program this and recreate Cebeci's axisymmetric solver, which was used to design the aerodynamics of a lot of missiles that are even flying today, and some aircraft. Some other notes, there's just some other little small transforms. And you have the notes, so I'll just kind of scroll through these and point out any important things. But I've said the major important parts that I wanted to talk about this. There's maybe a few other little tidbits about the eddy viscosity, and I'll just see if I want to make any notes about that quick before we move along. Yeah, one note, of course, is you can take that and set k equals 0 for 2D flow, and k equals 1 for axisymmetric. I already noted that. Oh yeah, for laminar flow, let's just say I had this general solver. I would simply set epsilon m to 0 and run my solver one more time, and I would recover the laminar flow solution. If I wanted an incompressible solution, I could still use my solver as it is, just let the velocity and Mach number at the edge be small, and I would recover an incompressible solution. There'd be no difference. This density would only vary a little bit. And one other thing is this all depends on transformed boundary conditions. And in your notes, which I don't think I want to talk about today, this is all the notes on how to take the original boundary conditions and transform them. So it's only, a half a page of little notes. Because if you're transforming your governing equations, you also have to transform your variables for the boundary conditions and initial conditions. And this whole thing is easy to march downstream from, say, your initial flow field. And of course it's fast, which makes you happy. But it does have some restrictions. And the major criticism of Cebeci-Smith's model is that it does depend on some tracking known values of boundary layer thickness and some wall statistics. And that's why people like Spalding came along and tried to use local properties. But they ran into more difficulties and they produced less practical models. So like I mentioned on Thursday, we're going to look at these papers and dissect them together and talked about practical predictions from Cebeci-Smith's approach. Okay, so thanks for your time today.